And so if you're thinking about the log of 1 plus x over 1 minus x, you remember we were doing that because if we took x as a fraction like 1/3, then you're talking log of 4/3 over 2/3, which is log 2, and you get a reasonably efficient way to compute log 2. If you were here yesterday, you remember that if you try to compute log 2 as the alternating 1 minus a half plus a third minus a fourth and so on, you do partial sums more or less forever before you get anywhere close. So if you're using Maple, you can produce the Taylor series. There are two commands you can use. If you've defined the function like this, you can either say Taylor and then your f of x that you have defined, then the x equals 0 is telling you that it's powers of x. If you wanted it in powers of x minus 1, then you'd say x equal 1 there. And then the 9 is how many terms altogether. So thinking of a polynomial, the first term is the constant, the second term is first power, so that means you'd have a polynomial through x to the 8th power if you typed in a 9. It'd be 9 terms. With a polynomial, the number of terms is one more than the degree. Line graph is first power, but 2 terms. Quadratic is second power, but 3 terms. See, I've been flying enough that I do like they do when they're reading all the rules and they point to the exits and all that, you know, the game if you fly any. So that over time, that kind of stuff rubs off. So we all have the flight attendant culture if we fly anywhere. Anyway, line 2, you see the terms. Now, I said it was a polynomial of degree 8. You don't see an x8. That's because with this particular function, the coefficients are 0 for all of the even order derivatives and even powers. And then that O of x9 refers to the error between the polynomial there and the true function. And we'll talk about what that means next week. Remember, we still have 2 more weeks of class. So we're not doing everything yet, but that's part of how Maple does it. So just think for now it has something to do with the estimating the size of the error. Okay, now what I did for line 3 is not the only way to accomplish what it does. What it accomplishes, let's look at what you get before you worry about the detailed command. What it's doing is it's defining g as the function of x, which is this polynomial that was produced in line 2. And the reason I've done that is so that I can get Maple to draw the graph of f, which is the true logarithm, and the graph of g, which is this polynomial that approximates it. So you see I've typed plot f comma g, and I put it in brackets so there's a sense of order there. So if I then say color and brackets red, green, the red goes with the F and the green goes with the G. In Maple, if you list functions in order inside of brackets and then color command in order inside of brackets, the first color is the color for the first function. The second color is the color for the second function. and so on. You also can do thickness in that same way, and you can do line style, solid graph, or dots or dashes. And, anyway, the point I'm trying to make is that for most of that graph, you would think that it's all the same. If you look closely at the ends, you can barely see that there's red there. But between minus a half and a half anyway, you can't see the difference unless your eyesight's better than mine, which is very possible. But regardless of eyesight, they're certainly very, very close until you get close to the ends of your interval. So that means that your polynomial is a good approximation to your log. And so thinking that you use x equal 1/3 if you want this to give you log 2, the g now is this polynomial of degree 7, line 3. So g of 1/3, you see, if you have a computer, it'll tell you the exact fraction. If you ask the question with a fraction, 1/3, that's an exact fraction, you'll get an answer that's a fraction. If you want it in decimal form, you do EVALF. And that's floating. The F is floating point, so that means the real numbers in decimal form. So that's a quick way to convert that fraction to a decimal. And so you turn the page, and you see its value that it's telling you is 0.693134, which you recognize as being quite close to what we were saying yesterday is calculated value for natural log 2. And so then what I did was to get Maple to give me a decimal value for the 9th derivative of this function, the original function f, not the polynomial for which the 9th derivative would be 0, but the original log of 1 plus x over 1 minus x. The reason for doing that is that the error function depends on the maximum value of the derivative, and the order derivative is whatever the number is back in line 2 where you have the big O symbolism. So the big O symbolism, big O, in mathematics, this type of way to write the error has two forms. A large 0, like you see there on line 2, we call big O, and a small-sized one that we call little o. And the meanings of those things are things we'll talk about next week, so don't worry about it. And none of that stuff's on the final, so you don't really have to worry about it particularly. But anyway, I'm saying it the way you would if you were trying to teach a math class. So anyway, the big O error formula depends on, if it says big O of x9, it's the product of the maximum value that the 9th derivative could have times the x, the place where you want the error, which would be 1/3, say, to the 9th power divided by 9 factorial. And as it turns out, you see, it's a pretty small number. So anyway, line 6 on the back of the first sheet of paper, one of the nice things about Maple or Mathematica is you could get it to tell you a ninth derivative without writing through all the steps as you would without a computer. And then if you want the value at 1/3, you type what you see there, EVALF, so it'll be a decimal, the ninth derivative of f at 1/3, and you see line 6. Okay, and later on, further down the page, I use the number. Then the next thing I did was the Taylor series, again, powers of x, and 10 terms, so what it does is get the polynomial through x ninth. And now my error is related to the 10th derivative at 1/3 and the x minus a to the 10th divided by 10 factorial. You notice if you're going to divide by 9 factorial or 10 factorial, you're going to have a pretty small error because those are big numbers. So again, I've defined g. Now it's this polynomial number 8 through x9. So it's a different g than on the previous page. And again, I'm plotting the logarithm and the polynomial of degree 9. And if you notice, if you compared the pictures, the interval is wider in this second picture before you begin to see a hint of red right at the end. But the two graphs are both there, you see. It's just that the one is on top of the other. And so if you ask for the estimate for the log 2, which is g of 1/3, remember it's the g now that goes through x ninth. You get the fraction, which is 9, and then the decimal for that, 693146. Okay, so if you compare those with what we had for our work with log 2 yesterday, if you compare with your calculator value, you see that's pretty close to what the calculator would say. If you have your calculator, try log 2 and compare it with the value of 10. Okay, then when I write capital letter T, I'm talking about what are called Taylor polynomials, which is what today's class is about. So the first Taylor polynomial then is a polynomial degree 1, so it could be like a line graph. It could be a constant and then the whatever you get times x to the first power, and you turn the page, so you get to line 11, and it's just really the first term of the thing that I've been calling g of x. It's the 2x, and then its value is 2/3. So your first approximation to log 2 is that it's 2/3, which isn't too horribly bad. That's 0.666, and it's actually 0.69. Then the third Taylor polynomial is the one that goes through x cubed. So that's the first two terms of what we've been calling g of x. And you can get the fraction for it, and if you wanted, you could get the decimal. And then the fifth polynomial, T5, you notice that the way you get Maple to subscript is you type whatever the name is, and then brackets, and then 5. And when it's printed, you see it's printed as a subscript. If you look at the line 15, the 5 is a subscript. So then that's the terms through x fifth, and the value, line 16, is a fraction, and then the decimal, 693. Well, log 2 is 6931 change. So by the time you do the fifth Taylor polynomial, your answer isn't too bad. And then I have the seventh polynomial, which is the same thing as what I called G the first time on page 1. And line 20 is its value, 693134. And then the ninth polynomial is what I was calling G the second time, and its value is 693146. So these Taylor polynomials, as they're called, even when it's just powers of x, the language is to call them Taylor polynomials rather than Maclaurin polynomials. That's not up to me. It's like English spelling. Don't argue, just do it that way, right? It's as hopeless as trying to argue with a computer or with the Department of Motor Vehicles or something like that. You can't argue with these people. And so anyway, back again, let's see. I turned the page the wrong way, pardon me. All right, so then on the top of the back sheet of paper, line 24 is the value of the 10th derivative at 1/3 and the decimal. And again, the point is that your maximum error would be that number over 10 factorial times the x minus 1/3, where you're trying to calculate the error estimate, and the x would be any value that's in your interval, which is between -1 and 1. And when you divide that line 24, line 25 number by a 10 factorial, you're going to have a pretty small estimate of your maximum error next week. So the last picture then in this is the two graphs between the ninth Taylor polynomial and the true f of x, and you see again that you can just barely at the end see that there is starting to be a discernible difference in the graphs. So this is graphical evidence that the Taylor polynomials become very close in a geometric sense to the true function. Let's look at what we have today then. So you see, the first thing I've written is what I've been saying. A Taylor polynomial of order n, or the nth Taylor polynomial, is written like this. And so it is your Taylor series, except that you stop where you'd have x minus a to the nth. Whereas the Taylor series itself would not stop unless you were working with a function where from some point onward all the derivatives are 0. if your function is itself a polynomial, then the Taylor series will stop, because for a polynomial of degree n, the n plus first derivative becomes 0, and the rest of them are 0. So some of the coefficients here in your Taylor polynomial may be 0 at the particular value of a. That is the case with what we've just been talking about, with that the series for log of 1 plus x over 1 minus x, half of those derivatives turn out to be 0, and you just have the odd exponents, as you see. So the final result that you have may be a polynomial with degree that's less than n, even though it's for the nth Taylor polynomial. You see, you have that with what we've just been doing, because if you look at my command, if you go back to your first page, and I have Taylor f of x, x equals 0, so it's powers of x, comma 9, okay. So that's really wants the 9th Taylor polynomial, which would be degree 8. Remember, when I say the 9th Taylor polynomial, I mean it has 9 terms, theoretically, including the constant, so it's a polynomial of degree 8. Like the first Taylor polynomial is constant plus something times x, okay? Well, if it turns out that that something, the coefficient of x, which comes from the first derivative, if your first derivative happens to be 0 at the a value, then all you see is the constant. So it is here. Your 8th derivative would be 0 for this function, and so all you see is a polynomial of degree 7, but you still did it, it's just the value was 0, or the machine did. And then the error term is degree 1 more than whatever you could say is your polynomial number. So that's what I'm talking about here. So the graphs approximate the graph of f of x, like we've been seeing in the pictures. When f of x itself is a polynomial, p of x, with degree n, then the nth Taylor polynomial in powers of x minus a will be another polynomial of that same degree, and they'll reduce to the original. So there's a question on the final, not your take-home final, but the other one, which is that type. It's question number 16. So what they give you there, this is your function. You see, it is itself a polynomial. And they say a equals 9, so they want you to rewrite it as another polynomial in powers of x minus 9. So you start out to produce a Taylor series, just like we've been doing. So you need f of a, where a is 9. So put the 9 in, 81 and 9 and 1, so that's 91. Then you do f prime, which is 2x plus 1. Take its value at 9, so that's 18 and 1. And then f double prime, and you get a constant. So f double prime of 7, 8, 9, 10, no matter what, the value is still 2. So then T2 is your Taylor polynomial built like the first 3 terms of your Taylor series. So it's your f of a, over 0 factorial. It's f prime of a, which is 19 over 1 factorial, x minus a. Then it's the 2, which is f double prime over 2 factorial, x minus a squared. And you see all higher derivatives are 0. And so, what do you get? 2 over 2 factorial is 1. So you get x minus 9 squared plus 19 x minus 9 plus 91, which is the answer that they want. Notice that this would reduce back to the original if you want to reconcile or check. Because you see, if you take this and square it out, you get x squared minus 18x plus 81. Then you have 19x minus 19 times 9, which is 171. And then you have 91. And so you have x squared, 19 minus 18, which is x. This pair is 172 minus 171. So you can rewrite then your x squared plus x plus 1 to this. This is important in the differential equations class to be able to do this. I can't really explain why it's important without teaching that class, but in working with what people call the Laplace transform, which is a name you may have heard. You use Laplace transforms to solve electric circuit problems. You often do want to be able to carry through this kind of thing, where you start with a polynomial, say that's powers of x, and you want to rewrite it in powers of x minus some other number, like x minus 9. So there is more point to this than you would suppose. Anyway, you have no excuse for missing this problem on the test, okay? I've told you the problem number, and I've told you the answer. And if you still can't get it right, I shall grade with no mercy, right? Okay, so get that one, all right? Anyway, these problems, the homework in section 10.8 wants you to do, for problems 1 through 10, they want you to do the 0 order, first, second, and third Taylor polynomials. So, for example, with problem 1, we have e to the 2x, and we want powers of x. So powers of x minus a, where a is 0. So these really are Maclaurin polynomials, except that the book doesn't call them that. So T0 then is f of a, e to the 0, so it's 1. T1 would be, well, to do T1, you need f prime. And so your derivative is 2e to the 2x, your chain rule. And f prime of 0 then is 2. So your T1 is your f of 0 over 0 factorial plus your f prime of 0 over 1 factorial x to the 1 power. So this is like a line graph. Works out, you see, to be 1 plus 2x. As you go, T0, T1, T2, say if you were building T2, you're going to build on the T1, that's not going to change, and then really it's T1 plus the second derivative over 2 factorial x squared. If you want to look at it that way. You don't really have to repeat everything each time. So your second derivative then of this which of course is your derivative here, brings down another 2. So you get 4 e to the 2x, and at 0, you just have the value of the coefficient. So your T2 will be, repeat this, 1 plus 2x, and then your coefficient here, 4 over 2 factorial x squared. And you can simplify to that. So it's a quadratic. And then T3 will be this quadratic plus what you get from the third derivative over 3 factorial. Okay, your third derivative is going to bring down another 2, you see, from here, derivative of this, so that'll be 8, and the e to the 2x. So your T3 will be the 1 for 2x, the 4x squared over 2 factorial, then the 8 x cubed over 3 factorial. Of course, it's times e to the 0 power, which is 1. So it would be a cubic like that. So I have another handout here, which surprises no one. If you look at the second set of maple, you see the first thing I've done is what we just talked about. My function is e to the 2x, and then if you want maple to do these Taylor polynomials, so you can say Taylor x equals 0, so that's powers of x, then 1 would be your first Taylor polynomial, so it's 1 then. Then series, then 2, second Taylor polynomial, 1 plus 2x, then the third one, and then, well, actually the order of the polynomial is 1 less than that number. That number is how many terms, so really the line 2 is the T0, and the line 3 is the T1, and the line 4 is the T2, and the line 5 is the T3, which is the degree of the polynomial. And then the n in your command is really the order plus 1, which goes with the order derivative in your error formula. So it's unfortunate that the way maple is set up is one off of the subscript you use on the order of the polynomial, but that's the way it is. It's like so many things. Okay. Just a second here now. So then take a look at this one, at problem 4. So we have log of 1 plus x, and a equals 0, so it'll be in powers of x, and they want the Taylor polynomial. So f of 0 would be log of 1 plus 0, which is log 1, which is 0. So then f prime would be the derivative, which, as you know, is 1 over times the derivative of the x. So f prime of 0 is 1. So your T1 then would be 0, which is your T0, plus your value of your derivative over 1 factorial, and then x. So it would just end up being x. Then f double prime would be the derivative here. So I would rewrite with a negative exponent, use the chain rule. I would never use the quotient rule to do derivatives if I have a constant for the numerator. I would rewrite with a negative exponent and use the chain rule myself. You can do it either way. And so then you get minus 1, whatever you have, new exponent is 1 less, times by the derivative of what's inside parentheses, which is 1. So you get something that looks like that. And so your second derivative at 0, put 0 there, is minus 1. And so your T2 is your T1, which is really just x, plus this next derivative at 0 over 2 factorial x squared. So it's finally x minus x squared over 2 factorial. Then if you want your third derivative, if you go from here with the negative exponent, you're doing the derivative of minus 1, this with the negative exponent. So you have the minus 1, you bring this down, you notice you're getting a pattern here that looks very much like 2 factorial. And you notice here you have 2 minuses, so it's plus. Then the new exponent is minus 3 times by the derivative of what's inside parentheses, which is just 1 in this particular problem 4. So the third derivative then is the 2 factorial times this, or this way. The value at 0 is just 2 factorial. So your T3 is 0, which is your T0, plus x, so that much is T1, then minus, this one was a minus, 1 over 2 factorial x squared, so this part here is your T2, and then this, the 2 factorial from here, which is your value, over 3 factorial from the pattern of the series, x cubed. And that'll simplify to something like this. So you're getting x minus x squared over 2 plus x cubed over 3. And that's the same Maclaurin series that we had when we worked with this yesterday for log of 1 plus x. Yesterday we got the start of this same Maclaurin series by taking the geometric series, if you were here yesterday, and integrating that. We wrote out the geometric series for 1 over 1 plus t, which was 1 minus t plus t squared minus t cubed. And then we integrated those 0 to x, and integrated what they equaled, which was the 1 over 1 plus t. So this gave us the log of 1 plus x, and this gives you x minus x squared over 2 plus x cubed over 3 minus x fourth over 4. So the Taylor series for an analytic function is the same whether you get it by doing the derivatives like this, or whether you get it by some other means like starting with a geometric series and then integrating term by term or differentiating term by term. And it's often less work to start with a geometric series and play games with it than it is to actually grind out the derivatives. But for the same function and the same powers of x, or powers of x minus a, if a isn't 0, there is just one Taylor series or Maclaurin series, depending on whether it's x or x minus a. No matter whether you do it through the derivatives or do it through some kind of an integrate term by term game. Okay, so I think we have this, don't we, on the handout. Let's see what we have here. Let's see, on the first page, this is the second set of maple that you just received. we wrote out the Taylor polynomials for e to the 2x. And then line 6 is this cubic Taylor polynomial for it. Let's see. Yeah, that's the one for the f of x. And then my graph is comparing the graph of the f, which is e to the 2x, and the g, which is this 1 plus 2x plus 2x cubed. And you see that they don't match all the way, but in between about minus a half and plus a half, they match very well. Generally, a Taylor series or a Maclaurin series will match the function that it's supposed to represent close to the a when it's in powers of x minus a. Whether the a is 0, and you're talking powers of x, or some other value. So then look at line 7. My f is the log 1 plus x, and then I ask for the series in powers of x, and you see if I say 4, that means that the thing's going to be cubic, and then fourth order error term. So line 8 ought to be the same as this is, and happily so it is. It's always nice. And so then my unapply command is a way to take the polynomial in line 8 and make the thing into a function so that I can get Maple to graph it. And you can either do the command as I have been, the unapply convert series to polynomial, all that, or you could just simply say g colon equal x arrow and type the x minus a half x squared plus a third x cubed. That's all I'm accomplishing there. And then if I turn my page, what I compare is the graph of the cubic polynomial, which will be the green, with the graph of the logarithm of the 1 plus x. And you see that between x equals 0 and about a half, it's a good approximation. And then as you go further away from the 0, then the polynomial no longer is a good approximation. This is always what you're going to have when you're trying to take an analytic function and represent it as a polynomial. No matter what degree polynomial, eventually the graph of the original function and the graph of the polynomial will be different, but they can be essentially the same for a long, long way. Okay, so then look at the next one, problem 7. So they want the polynomials for the sine in powers of pi over 4. So you'd use these polynomials if you were trying to compute sine and you were working with angles that are in the vicinity of pi over 4. Remember that in calculus it's always radians, because the derivative of the sine is not cosine x unless you're in radians. If you're in degrees, it's pi over 180 times cosine. And so if you want to look at it this way, people cooked up the radian system so that they wouldn't have to say times pi over 180. with everything they did with derivatives of trig functions. So anyway, what the people who made the trig tables did was to work with radians and then convert 4 degrees. So f is sine x and a is pi over 4. So t0 then would be just your f of 0. Well, no, it's not f of 0 now, it's f of a, which is f of pi over 4, and that's root 2 over 2. See, this is not a Maclaurin series now, it's a Taylor series, because it's powers of x minus pi over 4. So the pattern of derivatives, if you're doing this by hand, you have sine, cosine, minus the sine, minus the cosine for the order, derivative order 0, 1, 2, 3, and then you repeat yourself, because the derivative of this would be back to sine. So the order 0 derivative is the same as the order 4, and again, that's root 2 over 2 at this place, at this a value. And the first derivative in order 5 repeat, and second derivative in order 6, and third derivative in order 7. So you add 4 up here, and you get another column. So there are 4 answers, plus and minus root 2 over 2, if you're at 45 degrees. That's a very special case. That's the only place where you're going to have the sine and cosine equal value at the same point. And so your T1 then would be your sine of 45 degrees plus the derivative, which is also this number, your cosine, times x minus a. And then your root 2 over 2 is a common factor. So you can say it's this times 1 plus x minus pi over 4. And if you wanted to, of course, you could combine the 1 and the minus pi over 4, but I'd leave it like that if I were doing it. For your second Taylor polynomial, you have your sine of pi over 4, your cosine of pi over 4, x minus a, then your third derivative minus the sine, so minus root 2 over 2, then x minus a square over 2 factorial. And then if you want your third Taylor polynomial, you have all this again, and then you have your next derivative at pi over 4, which is this cosine, then x minus pi over 4 cubed over 3 factorial. So then look at the maple. So line 10, f is sine x, and you can either type Taylor or you can type series, either way, and then the f of x, and then where you're evaluating the derivatives. See, the x equal pi over 4, and then again, that means the polynomial is degree 3, and that it's the polynomial with 4 terms in it, if they're all there. And it means the error estimate would be involve the fourth derivative. So you see the line 11 then, you notice that this 3 factorial is 6 times 2 is 12. So you have minus root 2 over 12, which is the way Maple writes it. This right here is the same as what you have on line 11 for the coefficient of x minus pi over 4 cubed. And then your error term will involve the fourth derivative. Again, we'll talk about the error estimates next week. So then my unapply thing again is simply defining the polynomial of degree 3 as the function g, and then if you want to plot the sine, which is f, and the cubic polynomial, which is g, you turn the page to see what you have, and the what I've been doing consistently is the G is in green, G for green, of course. And again, you see that they are different graphs, but between somewhere near 0 on the left and somewhere past 1, remember that would be 1 radian, on the right, you can't really see the difference. Okay, then suppose you look at the group 11 through 24. In the homework, they want the Maclaurin series. So with 11, you have e to the minus x. So e at 0, that's e to the minus 0, which is 1. Then your derivative is minus e to the minus x. Your second derivative is plus. So this alternates between e to the minus x and minus e to the minus x as you take derivatives. So your coefficients at 0 will alternate between 1 and minus 1. So when you have an odd order derivative at 0, you have minus 1. When you have an even order derivative at 0, you have plus 1 for your coefficient. And you're talking in Maclaurin series, so it's powers of x. So you go 1 minus x over 1 factorial plus x squared over 2 factorial like this, which you could also write this way. So what you have then is an alternating power series like this. If you look at 13, you have a little more work here. You have the 1 over 1 plus x, and so you're messing with these derivatives again. So again, rewrite this with a negative exponent, I would, and then you see f prime and f double prime and so on. So what you're getting is a pattern with alternating sign and a factorial as your coefficient. So the nth derivative pattern, if you begin with n equals 0, is going to be sine alternator n factorial times 1 plus x to the minus n plus 1, which is in parentheses. That is part of the factorial symbol. Maybe it didn't print too well, it's kind of out of place. Okay, it's the factorial symbol, right? Definition. Okay, so you see how the pattern would go. If n is 1, you'd have minus 1 to the 0, 0 factorial, your 1 plus x, and then this exponent would be minus 1. So it's 1 over 1 plus x. So that's your original, that's your 0th derivative. Then first derivative, you'll have a minus here, 1 factorial your 1 plus x to the minus 2, like that. Then next you'll have plus 2 factorial, 1 plus x minus 3, then minus, and so on. So if you want the Maclaurin series, as opposed to getting this through using a geometric series, then your coefficients, which look like minus 1 to the n over n factorial, you'd have your f of 0, which is 1, your f prime, which is minus 1 over 1 factorial. These come because you're doing the Maclaurin series, and the rules for the series are always that you're dividing by these factorials here. So the point I'm trying to make is that the pattern of these derivatives puts the same factorial in the numerator that you have in the denominator. See the match. So that what finally happens is like that, and you produce the same thing as if you took the geometric series with common ratio minus x, for which the sum would be 1 over 1 minus the common ratio. So what I'm showing is that you could get the series for 1 over 1 plus x either as a geometric series where you did long division, 1 plus x into 1, see, like this. You could do this. You could get your series that way, which is then the geometric series for 1 over 1 plus x, or you can actually go through the derivatives thinking of this as the function of x for which you can do these derivatives, and either way you end up with the same thing. And that's again what I was saying, that the Taylor series for an analytic function is the same no matter what you do, whether you play geometric series-based games, perhaps with integration term by term like we did here, or could have done here, or perhaps just from algebra where you do long division and don't stop. You get the same series. Okay, let's end with another polynomial game. This one is a little more complicated. This is one of the homework problems. And they want this in powers of x minus 1. So that means the a at which you evaluate the derivatives will be 1. So it's easy to do the derivatives. And your third derivative is constant, so of course it stops. Evaluate at 1. So your f of 1 is 2 and 3 are 5 and 1 are 6 minus 8, so it's minus 2. And then your f prime is 6 and 2 and 3 is 11. F double prime is 14, and f triple prime is the derivative of the 12x, so it's 12. And then they'd stop. So your Taylor series would be, in this case, the same as the third Taylor polynomial because your fourth derivative would be 0, so you'd have a 0 error term then. Your error is proportional to that next derivative, and some more things, but if your fourth derivative and higher are 0, then that means you had a polynomial of this degree. So then what you want is f of 1, because it's powers of x minus 1, f prime at 1 over 1 factorial x minus 1, and so on like that. So putting in the values, you could say this, or simplify, because 2 into 14 is 7, and 6 into 12 is 2, and write something like this. This is about what the answer would be in the book if it were an odd number. Now, just to prove that it really works, if you wanted to, you could first, usually with polynomials, you put the what would be x cubed first. So if you turn this around, you put this first, and that second, and this third. Then if you cube this out, this is what you get. If you square this out, this is what you get. And then multiply with the distributive law here. If you multiply it all out and cancel out like terms, you'll get back to where you started. So there's your 2x cubed, and you have 7 minus 6 is 1x squared, and you have 11 and 6 or 17 minus 14 is 3x, and then you have the 7 minus 11 minus 2 minus 2 is minus 8. So you can see it works. Again, being able to rewrite this in this way is something you would want to be able to do if you take the differential equations class, or if you take the systems and circuits class. They do Laplace transform games in circuit analysis, and so sometimes you want to be able to do this kind of thing. Well, I think that's enough for this week, and we'll continue on in the same chapter next week, the week after.